Yeah. Okay. Cool. So I'll be sharing my screen now. Yeah, I hope my screen is visible. Also, I am audible, right? Okay, so I'm guessing I'm audible. So basically, before starting anything today, so this is the last session that I'll be taking for this course, and probably after this you'll be appearing for your examination also. Those of you who have applied for the certification, they will have to appear for the examination in this course. So today I will not be discussing anything. So I'll be discussing something. I'll be discussing week 10's content. Okay. So week 10's content I missed. Pardon for the voice. Pardon for the noise adjacent to my room. But yeah, so I was not able to discuss week 10's content. So today I'll be discussing that over and moreover I'll be any doubts are welcome. Okay, any doubts pertaining to any of the content that was taught any other weeks. Okay, right from week 1 to week 12, whatever the whole course basically. If you have any doubt, you can ask me now. Okay, so this is the last session that I'll be taking today, and it will not be that long also. But I'll be trying to wrap up quickly. I'll just be discussing some questions related to week 10, and that's all. And then I'll be basically wrapping up the course. So I told that I'll be discussing some questions which will help you in basically I told you that I'll be discussing some previous year questions, but sadly I was not able to get my hands on those questions, so I'll not be discussing them. But it's okay because you see all the questions that were discussed in the sessions that I was taking earlier. Uh, I mean, you will be able to solve based on those questions if you understood them properly. Also, my colleague he was taking the sessions on Fridays. Sorry, yeah, Fridays, right? So basically, he also covered a lot of other questions. So you should be fine if you watched if you attended all the sessions, you should be fine. Should not be able to suffer much. I get you should not be able to suffer because you already have been exposed to a lot of questions. Now, I will not even be summarizing the whole course because my colleague he summarized the whole course day before yesterday. So I'll just be covering week 10. Okay, today. So some of you asked me to put some questions based on the uh, op amps in week 10. So I have put those questions here. I'll be discussing those questions now. If you have any doubt, you can interrupt me in between and you can ask me. Okay. All right. So before doing anything, let's again let's do some formal introductions. Okay. So this is NPTEL course Basic Electrical Circuits, and it was taken by Dr. Gajendranath Chaudhary. He's a faculty member in Department of Electrical Engineering at IIT Hyderabad. Myself, I am Mayank Anupam, and I am a PhD student and a PMRF scholar. Currently, I am pursuing my PhD in Electrical Engineering at IIT Kanpur. Okay, so this concludes the introduction. Fine. So we have the first question here. Yeah. So the first question says that basically in the circuit given below. So this is the circuit here. Okay. The op amp is ideal. So basically you have to consider this op amp. This is an ideal op amp. You remember what is an ideal op amp, right? We already discussed this earlier. An ideal op amp, the gain is infinity, right? The ideal op amp gain is infinity. All right. So in an ideal op amp, these two ports are these two inputs, they are virtually shorted, right? So they are virtually shorted, these two inputs. So whatever is the voltage here, same voltage will appear here. Okay, cool. So the other thing is that yeah, now the voltages, the expression of voltage is given by VB and V naught are given to you. This VB here and V naught, they are of this kind. The voltages are of this kind because the input is of this kind. Okay, sine root 3 t 2 into sine root 3 t. This is the input of the to this particular op amp, to this particular system. Okay, and the two voltages VB and V naught, they are of this kind. So now you have to find out what is the value of A, what is B, what is theta and theta 2. Okay, so tell me, what should I do? Yes, so this is basically, you remember that for any first order circuit, what was the condition? I mean, if you excite so basically this is the sinusoidal steady state that they are interested in. Okay, the expression of voltages is given by this kind. So these are steady state voltages. Okay, so they are actually the question is actually the question is asked for you to find the steady state solutions here. So we know that steady state solution is what? It is the forced response, right? It is actually the same as the input, which is scaled and then has some phase lag or lead, whatever, compared to the input. The input, the frequency will be same as the input, but there will be some scaling factor involved and there will be some phase information, right? So let's do that. So first, so this is the 2 sine root 3t. This is the voltage here, right? So what will be the voltage here at this point? Yeah, come on. What will be the voltage here? Okay. So the voltage at this point here, it will be what? So let's consider only this section here, right? Because you see that this guy here, this whole other network, this will not affect the voltage here, right? Because because the current that is going to go inside will be zero, right? So there, if I only consider this, the green, the network highlighted, network which is encircled in green, so only that we can consider alone, right? It will not matter. It will not affect our calculations. Okay, so let's consider that network only. So this is the situation here. We have this, and then we have this R, and we have this C. The C is 2 farad, this R is 1 ohm, right? So first order of business is to find out what is the RC time constant, right? Correct. The first order of business is to find out what is the RC time constant, isn't it? So what is the RC time constant here? So this is R, this is C. So what is RC? 2, right? 2 seconds. RC is 2 seconds, right? So what is the response of this voltage here? Let's call it some V intermediate. Oh, that is not a good name. So let's call it some Vx. Okay, let's call it some Vx here, this voltage. All right. Yeah. So what will be Vx? Vx will be 2 sine. So basically the magnitude of the sinusoidal input is 2, right? So magnitude will be what? Scaled by a factor 1 plus omega square r square c square, right? Correct. So it will be 1 plus 3 into 1 into 4, correct? And then the sine term here will be root 3t, and then there will be a minus of how much? Tan inverse omega times, this is omega, right? Root 3t, omega times r times c, right? 2, isn't it? And this is in radians, okay? Mind it. Everything here is in radians. So this will be how much? 2 by 1 plus 12, 2 by root 13, right? And into sine of root 3t minus tan inverse of 2 root 3. So this is the voltage that we'll be getting at this node Vx, right? At Vx. Now the Vx voltage, it will appear same here, right? The voltage at Vx will be same as this voltage here. So this will also be Vx, correct? So 1 second, let me turn on the fan. Yeah, so this node voltage here is also Vx, right? So what is the voltage Vb in terms of Vx? So it is a so this is very easy, right? If this is Vx here, so we can write simple KCL, right? So let me now remove these highlighters here. So the KCL will be what? The current entering this node from this direction should be equal to the current leaving this node, right? So this will give me what? So it will give me Vb minus Vx divided by 3 should be equal to Vx by 1, right? So this will give me Vb should be equal to how much? 4Vx, isn't it? Right? So with this information, so what will be Vb now? 4 times Vx. What is that? 4 into 2 divided by root over 13 sine of root 3t into tan inverse of 2 root 3 volts, right? So we have found out what is Vb here. Okay, correct? So tell me what is theta 1 here? Yeah, so tell me what is theta 1? Vb was of this kind, right? And this was also equal to 8 by root 13, right? Yeah, this is also equal to 8 upon root 13 into sine of root over 3t minus tan inverse of how much? 2 root 3. So our theta 1 is what? Minus of tan inverse of 2 root 3, right? Cool. And what is our A? A is 8 by root 13 and the units will be volts, right? Okay, good. Now now tell me what will be V naught here. Once we have Vb, what is the relation between Vb and V naught? The same kind, right? Again, it is a sinusoid, sinusoidal input here. The Vb and Vx relation is what? So if this node is Vb and then this is an RC network again, first order RC circuit, and this is our V naught here. So if it is this node is Vb here and this is how much? 2 and 3, right? So this is 2 ohms, this is 3 farads. So again the same thing, right? So what will it be? What is Vb? Vb is as given here, right? So what is V naught? So first order of business again here will be RC time constant. What will that be? 6 seconds, right? Correct.
Got it?
uh, you have some doubt, Javed? Did you ask any doubt, Javed?
No, sir. No,
Yeah.
sir.
Okay, thank you, thank you.
No, no, no,
Okay.
sir.
Yeah, yeah, thank you, thank you, thank you, thank you. All right. So now we have this thing. Hmm. So now again the same thing, right? So VB is given by this quantity here. So what will be V naught? V naught will be basically the magnitude of V naught will be this magnitude of VB divided by 1 plus omega square r square c square, right? So it will be 1 over, or basically 8 by root 3, and that will be further divided by root over 1 plus, so this is 13, 1 plus 36 into 3, right? Yeah, yes, fine. And then there will be what? Sine of root 3t minus tan inverse of 2 root 3. This was the earlier phase, right? This whole quantity was earlier, and there will be extra phase lag, right? Minus of tan inverse of how much? Omega times, which is root 3 times, I mean root 3 times 2 root 3. Oh, my bad. Sorry. Root 3 times how much? R into C, right? It is 6, isn't it? So this is the other one. Basically, this is the V naught one. This is V naught. So okay, so let's simplify this. How much will this become? 8 by root 13 into, and this is 36 3 is how much? 108, right? So this is 109, and this is sine of root 3t minus tan inverse of 2 root 3 minus tan inverse of 6 root 3. So this is the net voltage. So what is B now? Yeah, so what is B now? B is 8 divided by root 13 into root 109. 8 by root 13 1 by 109 root over 19. Oh sorry, 109 into sine of root 3t minus tan inverse of root 2 root 3 minus tan inverse of 6 root 3. So from here B is equal to 8 by root 13 into root over 109, and then theta 2 is tan inverse of root 3 minus tan inverse of 6 root 3. Alright, so I hope this clarifies. I mean, you understood, everyone understood this one. So with an ideal op amp, the situation was not that difficult, because you see, an ideal op amp simply means that gain is infinity, and whatever voltage appears at one of the, basically the two input terminals, they are virtually shorted in case the op amp is properly connected in negative feedback. Then the two inputs are virtually shorted. Okay. So why do I say that they are virtually shorted? Because you have not put an explicit sort between these two nodes, right? You have not connected them with wires. But even then, the two voltages are always the same, right? These two voltages are always the same, irrespective of the fact that you have not put any explicit connection here, right? There is no connection here, but still they have managed to be same. So that is why you say that the two nodes are virtually shorted. The two inputs are virtually shorted when the uh, when op amp is infinity, which happens to be a case for an ideal op amp. Fine. Let's move on to other question. Yeah. In the circuit given below, the op amp is ideal. The expression of voltage is given by. So basically, here also the same kind of question it is also. Okay, this is also the same kind of question. Here, the input voltage is basically the two input voltages here. Okay, and the two voltages that they are interested in are this V and VB. Okay, now V and VB move in this fashion. So basically their voltages of this kind, the one that is shown here, and it makes sense also, right? So there are two different kinds of excitations in the input, right? One is pure sinusoid, one is exponential. So you also expect two different kinds of I mean the overall voltage at any node should be composed of a linear combination of these two, right? Because the input is a linear combination of exponential and sinusoidal, and since this is overall a linear circuit, so you expect that the response of any node will be again the linear combination of these two voltages only, these two excitations only. So that is why you see that there is always a e to exponential and pure sinusoid here, right? So cos and sin are basically the same, pure sinusoid only. Cos is just a 90-degree phase uh, shifted signal, phase shifted version of sinusoid, right? That is why they are they are basically the same thing. Cool. So let's figure it out now. Okay. So tell me. So since I know that the circuit can be the circuit here can be solved in two ways. Okay. So I mean the circuit here can be solved in two ways. So let's so one way would be how? One way would be to convert this sinusoid, write the sinusoid in terms of uh, basically one way would be how one way would be to find the response of the circuit individually due to this exponential and due to this sinusoidal, and then add the two, and you can do that because it's a linear circuit, and you can you remember the principle of superposition, right? So you can basically one way would be to do this. So method 1, so find the response of the circuit individually due to the exponential and the sinusoidal input, and then add the two responses, all the right. So you can do this, we can do this. Why? Because the circuit is linear, and hence superposition is valid, right? So basically this is superposition. For any linear circuit, the response of the overall circuit to a linear combination of inputs, okay, independent inputs, is basically the sum of the responses of the circuit to the individual inputs. Okay, basically here this is the overall input. The response of the circuit to this overall input would be what? To find the response of the circuit due to this, and then due to this, and then add the two. Okay, so that is principle of superposition, and that can be applied here because the circuit is linear. All right, so now yeah, so tell me, what will I do? How will I do? You know the response of the circuit due to this exponential, isn't it? It's very easy, right? What is the response of the circuit due to exponential signal? So you see here, by the way, this is easy to see. What is the voltage here? Again, you have to assume that the op amp is ideal, which means that the gain is infinity here. Okay, and you can see that both of these op amps, they are connected in negative feedback. Okay, so tell me, what will be the voltage here at this node? So the gain is infinity, and the op amp is connected in negative feedback. That is why the voltage here, this node voltage here, has to be same as this node voltage, right? Which is 0. So this will also be virtually ground, right? The voltage will be actually 0 here, correct? Voltage here is 0. Fine. So what is in that case, what is VA? So whatever current this is moving here at this node we have to apply KCL, right? So whatever current is going this way has to go this way, right? There is no other direction that the current can move. So current entering this node has to be equal to current leaving this node, right? So again, do this the same thing. So what is the current which is leaving this node here? This is C, which is basically C is this 2 farad C. Okay, C times dVA by dt, and there will be a negative sign, right? Okay, let me make it more clear. This is C times d of V, this node voltage minus this node voltage, right? So 0 minus VA divided by dt. So this is the current leaving this node, right? This is the current. And what is the current that is entering this node here? That is equal to V in divided by this 3 ohm resistance, right? V in by R, which is equal to V in upon 3, right? So these two have to be equal, correct? So we have V in upon 3 has to be equal to minus C dV upon, and what is C, by the way? C is 2 farad. This is equal to 2 times dVA upon dt. Okay. So now tell me, what is the relationship between VA and V in? So VA is equal to how much? V in upon 3 into 2, 6, right? And integral of this, isn't it? And since initial conditions are not given, right? Initial conditions are not given, so basically this will also be integrated, right? This is dVA, and between so basically time t is equal to 0, VA was equal to 0, and then time t is equal to some t, VA will be some VA, right? So this is simply an integral, right? So tell me, what will it be now? This will be VA is equal to 1 over 6 V in dt, 0 to t minus sign, right? So now it's very easy, isn't it? Now simply put V in here, the V that is given here, simply put it here, and then you can simply calculate uh, what is the voltage VA. Okay. Now similarly, tell me, what is the relationship between VA and VB here? What is the relationship between VA and VB? Let's find out. So if basically, so before that, you see this network here, it is also called an integrator, okay? Because now here you integrated it. So how is it an integrator? Let's see. I'm sure you must have seen it earlier. I mean, this is also covered, but I'll just put it here. Hmm. So this is infinity again. Okay, gain is infinity, and yeah. So what is the again the the relationship between V and V out? So we just saw that, right? So it's actually V in is first converted. You see the voltage here is zero, right? The voltage here is zero. So that is why the current, the voltage here V in is first converted into current, proportional current by this relationship V in by R, right? And then that current is being integrated by this capacitor. Hmm? So the relationship between V in by R, this has to be equal to minus C dV out upon dt. So that is why our V out is what? Minus 1 over RC V in dt, right? So you can see that V out is an integral version of V in, isn't it? This voltage V out here is the integral of some integral of V in, right? Is proportional to the integral of V in, correct? So this is an integrator. Similarly, if there is a small change in the circuit, and then we'll get a differentiator. Let's see how we'll get that. So it's a V in here, and there's a capacitor here. Hmm. Yeah. So this is the situation here. This is the situation here. So in this case, what will be the relationship again? Again, it's the same thing, right? This voltage will be zero. So any current that is coming here has to leave this node like this, right? So the same thing here will be C times dV in upon dt, right? Has to be equal to minus V out upon R, correct? So here our V out is equal to how much? Minus RC dV in upon dt, right? So here we can see that the relationship is differential, right? V out, the voltage V out here is proportional to the derivative of the input voltage, correct? In on the other hand, in this circuit here, the voltage V out is proportional to the integral of the input voltage, right? So you see the difference. So only these two circuits are used here. So first the input voltage V in will be integrated here, and then that voltage will be again differentiated here. So V in and VB, there should be sine term, right? V in, if V in is sine, at first it will be integrated and it will become cos here at VA, and then again after differentiation it will become sine. So that is why you see V in here is sine and VB here is also sine. Whereas this term here VA here is the integral of V in, that is why it is cos, right? So now I will leave the rest to you. You can figure it out because I have given everything. There's just put some numbers and you'll be able to find the answers. Hmm. So is there any doubt in this particular question? I hope not. So this is hmm, yeah, another kind of question. The first order circuit again, but now they are asking the voltage across the capacitor for time t greater than 0. So this is the voltage at Vc of t that they are wanting us to find. So what is Vc of t as a function of time when time t is greater than 0? So here we assume that the initial conditions are 0. Okay, since nothing is given, that means the you have to assume that Vc of 0 has to be equal to 0. So if nothing is given in the question about the initial condition, you always assume that the initial conditions are 0. Okay, fine. Yeah, so this is the condition here. So tell me what will be the, how will you solve this question? You see the input is a multiplication of exponential and cosinusoid, right? But we are accustomed to seeing this kind of input, right? E to the power st. For this we know what is the response, right? So by the way, first let me see if so tell me what will be the response of this. If this current here is of the form e to the power st, then what will be the response here? Voltage V out. Yeah, what will be the voltage V out here? We know that a first order circuit, RC circuit, is what? The response at any of the nodes is a eigenvector, right? Sorry, exponential is an eigenvector for this particular this thing network, right? For any first order RC circuit, the exponential is an eigenvector. In fact, this statement holds for any this thing, for any linear time invariant circuit. Okay, not just first order RC circuit. For any LTI system, this statement holds that the complex this exponential here, exponential e to the power st, where s can in general be a complex number. Okay, this e to the power st is actually a eigenvector for that particular system. The output the response of that system to this exponential here will always be some factor multiplying that exponential again. Okay, so the response to this will be how, what kind? It will be I into r. So this, let's say this is I is equal to e to the power st. So I into r divided by 1 plus src, and the I will be I is equal to e to the power st. So it will be r into e to the power st divided by 1 plus src. Okay, so this is the response. All right, now, so but here you see this current here is not e to the power minus t only, it is also multiplied by cosinusoid here. So what should I do? So any ideas? I should first convert this cosinusoid into exponential only, right? So I know that 2 e to the power minus t, and cosinusoid is what? E to the power jt plus e to the power minus jt divided by 2, right? This is cosinusoid, isn't it? Correct. So this is what? This is e to the power minus t common 1 plus, or 1 minus j, right? Plus e to the power uh, minus t into 1 plus j, right? So these are the two inputs now. I have modified, or basically yeah, so I have modified my input signal here in this form, so that I can solve it. I have now converted it into a linear combination of two inputs which are now exponentials, right? and now I know the response of the of my system to these exponentials. I find them individually and then add them, because the circuit is again linear, so I can do this. So this is also e to the power st. These two are of the form e to the power st, right? Correct. Tell me, due to, so now I can use superposition, right? So if I do that, then due to, so I'll have to find out due to e to the power minus t, or I will take minus t inside, so it will become e to the power minus 1 plus j times t, and and e to the power t minus 1 minus j, and then simply add the two. Correct? So let's do that. So only due to e to the power minus 1 plus j t, what is the value? So you know that in this case, what is the s value of s? So if this is equal to e to the power st, right, we know the response to e to the power st, right? So what is the value of s in this case? Minus 1 plus j, right? So let's do that now. Let's just put the value here. So we'll get our v out is equal to r into, right, e to the power minus 1 plus j t divided by 1 plus, and what is rc? R is 1, c is 1, so rc is 1 seconds only. Correct? 1 plus s is what? Minus 1 plus j, and rc, so rc is again 1. So this becomes, and okay, so r is 1 here, right? Becomes e to the power minus 1 plus j times t divided by, so 1 and 1 cancel, so it becomes simply j. Correct? So this is the value of v out due to only the first input. Now only due to e to the power minus 1 minus j times t again. So if this is equal to e to the power st, that means s is equal to how much? S is equal to minus 1 minus j, right? So what is v out now? Same thing, 1 into e to the power st, which is minus 1 minus j times t divided by 1 plus minus 1 minus j times rc, which is 1. Correct? So this will come again the same, just with a minus sign, minus e to the power minus 1 minus j times t divided by j. Correct? So this is only due to the second input, right? Now overall v out will be how much? So let's call this v out 1, let's call this v out 2. It will be equal to how much? V out 1 plus v out 2. How did I come to know this? This is because of principle of superposition, right? Yeah. So what is the final answer now? So it is v out 1 is e to the power minus 1 plus j into t divided by j, and v out 2 is minus e to the power minus 1 minus j into t divided by j, right? So tell me, what will this be? So these and two these, there is a minus sign here, j comes out. Okay, j comes out, and e to the power minus t is common in both of these, right? So e to the power minus t also comes out over j. Then we have e to the power jt minus e to the power minus jt, right? So how much is that? This is 2j sine 2j sine t, right? This is e to the power minus t into divided by j and 2j sine of t, right? So 2 so sorry, j and j go, right? So it is 2 sine 2 e to the power minus t sine of t. All right. Okay, this is how we get it. So I did nothing but I just simply used principle of superposition. I converted this cos here in a form which is more suitable for us to handle. We could have always used the same e to the power minus t to cos t, the same thing, and then we could have solved the circuit by writing differential equations. But but why should I do that when I know the answer to a to a particular kind of to a particular kind of input? I know the response. I just want I it will just be better for me to convert my input into a more familiar form and then simply straight away write the answer, right? Okay, so any doubt here? Okay, yeah, I should try this question. uh, this also you should try. I mean, definitely should revise this question. But okay, so let me solve this, otherwise it will also be a good revision for you. This is too big. I should simply reduce the size here. You see, this is an inductor. Okay, this is an inductor here, this is an inductor here, and then there is a mutual inductance between the two inductors. You remember something of this kind? Mutual inductance, do you remember something of this kind? So this dot here and this dot here, and then there is a this kind of a this thing here, which shows that there is a mutual inductance between the two inductors, and that mutual inductance value is 2 Henry. So what kind of a, I mean, what will the relationship between the two this thing will be? Tell me. I mean, we just want to find out what is the steady state output voltage V out. I know VI, right? I know VI. I want to find what is V out. So tell me what will it be. So let's start writing. Before that, quick revision. So this is the situation, and we have dots placed like this. V1, this is V2, this is L1, this is L1, this is L2, and there is a mutual inductance M. So what was the relationship? Do you remember? It was V1 is equal to L1 di1 by dt, L1 di, so yeah, so I1 is like this and I2 is like this, right? So it used to be L1 di1 by dt plus M times di2 by dt. Similarly, V2 was L2 di2 by dt plus M times di1 by dt. This was the relationship, correct? Now, for this relationship to hold, the sign convention was like this, right? The dots, if they are placed in this way, so basically in the direction of dots only, the both the voltage and current should be in the direction of dots itself, right? So if the dots are placed in this way, the voltage and current has to be this way, right? You select one of the basically, what was the sign convention? When could you take positive sign here, plus sign here with M? When the current, if you have defined the current entering this first port here, the first inductor you have defined the current in this manner and the voltage in this manner, then the current and voltage relationship for the second inductor has to be in this manner only. Only then will this plus sign hold here. Okay, let's say if you did this, so this is your I1, this is your V1, this is L, this is L2, but now I2, let's say it is this is I2 and this is V2. So in this case the relationship will differ. Okay, in this case the relationship will differ. So now in this case you see V1 here is equal to how much? L1 times di1 by dt plus, or rather minus, m times di2 by dt, right? Similarly, what will be V2? V2 will be L2 minus L2 times di2 by dt plus m times di1 by dt. Okay, so this will be, I mean, the relationship will not hold if you try to define it in this manner. Okay, so this is the correct sign convention here. The moment you define a voltage and current relationship like this, okay, the voltage current relationship for the second one, for the second part is also defined by the direction, by the way the dots are placed. Okay, so here you see the dots are placed in this manner, here and here, right? And the voltage is defined in this manner. So this is V naught T, right? And this is VIT here, correct? And the dots are placed in this at these points here. And now I will assume the current to be like this. This is our I. Okay, this is our I1, and let's say this is our I2. Okay, all right. Hmm. Yeah. So tell me what will be the relationship between I1 and I2 first of all. You see that the current which is entering here has no other way but to go here only, right? In the has no other way but to flow through the 18 Henry inductor. So I1 has to be equal to I2, right? So first is I1 has to be equal to I2. Fine. Now let's write some equations here. So what is the current what is the voltage VI minus V naught here? So this is VI, this is V out. So voltage across this inductor has to be VI minus V naught, right? That has to be equal to L1. So this is L1, this is L2, and this is M. Okay, 2 Henry. So L1 times di1 by dt plus, whether it will be plus or minus, tell me. You see the according to our passive sign convention here, according to our sign convention for inductance, okay, if the current is entering in the first, do you have a doubt, Vinod? Okay. Oh, you were answering. Oh, yeah, yeah, it should be minus. Yes, good. So I just want to say why it should be minus. So basically, you see the according to sign convention, if the dots are placed in this manner, right? And if the current is entering towards the from the dot side for the first inductor, then the current should also enter towards the dot side of the second inductor, right? Only then there will be plus M. But in this case, you see the current is entering here in the first, for the first inductor, the current is entering towards from the dot side. However, the current is not entering from the dot side, right? It is leaving from the dot side for the second inductor. That is why it will be minus sign here, minus m times di2 by dt, right? And for the second one, basically the second inductor, the equation will be v out should be equal to L2 times di2 upon dt, right? Okay, and then again minus m times di1 by dt, right? So now this is the first equation, this is the second equation. So tell me what will be the relationship between vi and v out. So from this, v out is equal to L2 minus okay, sorry, yeah, and by the way, I2 and I1 are same, right? You already established that. So let me just replace I2 and I1 with only I1. So we have v out is equal to L2 minus m times di1 by dt, right? And so this is our third equation. Let's put this third equation into the first one. So we'll get vi minus L2 minus m times di1 by dt should be equal to L1 times L1 minus m times di1 by dt, right? That will give me, what will it give me? Vi is equal to L1 plus L2 minus 2m di1 by dt, isn't it? So yeah, and what is v so what is v2? V naught. Oh, by the way, what is di1 by dt here? Vi upon L1 plus L2 minus 2m, right? So what is v out? L2 minus m into di1 by dt, right? Which is vi divided by, so this is our fourth equation, so we'll just put it here. Okay, so vi divided by L1 plus L2 minus 2m. So how much is that? So L2 minus m into L1 plus L2 minus 2m times vi. So this is our, so if vi is 2 cos 2t, so you see, just put the value of L2 and m, L1, L2 and m, you will get what is the value of v out. Okay, fine. So if that is the case, okay, it looks like it's done. Okay, I guess this is it. I had only these questions to discuss today. Okay, let me see. I think one question was not refreshed. Why is this question not appearing here? Yeah, I have this question now. Yes. So this question is, in this circuit given below, the switch has been open for a long time, okay, and is closed at t is equal to 0. Then the voltage v of t for t greater than 0 will be what? So this switch here, it was open, okay, it was open for a very long time, and then it is suddenly closed. So what kind of a response, what will be the voltage for t greater than 0 will be? So first of all, this is very easy, and I will not be solving this. I'll just be saying, just be discussing how to solve this question. It's just that you see, when the switch was closed earlier for very long, okay, sorry, when the switch was open for a very long time earlier, so you see that the capacitor would have been fully charged, right? So this voltage would have been 4 volts initially, right? Right, and then suddenly this guy here is closed. So tell me something, the moment this is closed, what will happen? This 4 volt will start to change, right? Something will change with this. Something will happen to this 4 volt. It will not be 4 volts, right? In fact, after very long time, the steady state value of this voltage, steady state value of V of t will be what? Since this is shorted here like this, and there is a voltage control, sorry, current control voltage source here. What is Ix? Yeah, Ix is, what is Ix? Okay, Ix is the current flowing through this voltage source. Okay, Ix is the current flowing through this voltage source, Ix. So based on so basically this is the voltage control current, sorry, current control voltage source here, whose value is 2 times Ix. So this will definitely try to enforce and enforce its own but basically it will try to add its own masala, right, to this voltage, and this voltage will change after a while. Hmm. So so yeah, so in steady state what will happen, there will be some different voltage here, right, and that voltage will be given by what, this A, right. So you see, if Vt is A plus and B times e to the power minus Ct, at V of 0 will be A plus B, and V of infinity will be steady state, basically it will be A only, right. So you can find it out, it's very easy. Now the catch is to find C. So infinity, V infinity, how will you find out, by the way? Just have to short it, right? And at infinity, you know that this capacitor is no longer carrying any current, right? So Ix will be, all the Ix current will be flowing here itself, right? So with that you can solve, with that help you can solve this question now. The catch is to find this C, the value of this C. So how will you find C? How will you find C? Just have to do the same old thing, right? You have to find out the, basically the what is the order of this circuit? This is the first order circuit, okay? This will be a first order circuit. So you just have to find out what is the Thevenin's resistance across these two terminals. Okay, what is RTH across the two terminals? You find RTH, and C will be how much? C will be 1 by 6, which is R, sorry, 1 by 6, which is the capacitance C, times RTH, and then inverse of this. This will be your C. Okay. So when you find that, when you find RTH here, you'll be able to find the value of C, and then you'll be able to solve this question also. So I guess this is what I had to discuss today. If you have no other doubt, then I can maybe wrap up the session now. Do you have any doubt, anyone? So I see only one guy present here. So do you have any doubt? Okay, fine. So if you have no doubts, then basically we can wrap the discussion here at this point. So thank you everyone for being with me. The smooth conduction of this course, of the sessions for the 12 weeks that I took, and yeah, one extra week today. Thank you very much, and I hope you all do very well in your examinations. So okay, so see you in the next course that if you will be taking the next semester. Thank you very much. uh, all the best for your future.